Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's up everyone? Before we move on to today's show, I want to give you a heads up that we are back with another interactive podcast viewing party on Monday, May 18th. This time, I'll be joined by Emily Bender, professor of linguistics at the University of Washington. Our recent interview explored the question of whether linguistics has been missing from NLP research. We dig into questions like, would we be making more progress on more solid foundations if more linguists were involved in modern NLP? Or is the progress we're making, such as with deep learning models like transformers, just fine? We also explore issues like fairness, bias, and ethics in NLP, and more. Emily and I will be in the chat answering all of your questions about the interview. We'll begin the viewing party at 3 o'clock Pacific on Monday. You can head over to twimlai.com/376viewing for more details or to add it to your calendar. And now, on to the show. All right, everyone, I am here with Nataniel Ruiz. Nataniel is a PhD student in Image and Video Computing Group at Boston University. Nataniel, welcome to the TWIML AI podcast.
Thank you very much.
It is great to have a chance to chat with you. I'm looking forward to digging into our topic, which is some work you've recently done on disrupting deepfakes. But before we dive into that, tell us a little bit about your background and how you got started working in ML and AI.
Yeah, so the first kind of project that I did in AI was a computer vision project when I was doing an internship here at MIT. And it was about basically detecting diseases in cassava plants. And we were going to deploy the application in Uganda. So that was kind of like my first introduction to like deep neural networks and image processing type of stuff. And I thought that was incredibly interesting, just like the potential of these types of applications and this new technology, right? Or this technology that had been advancing like very recently. So I got really interested in it. Then I did my master's at Georgia Tech. So that was right after that internship. And then, so at Georgia Tech, I met a mentor and my professor there, who was my advisor for my master's, Jim Ray. And I joined his group and did a lot of stuff. So I got interested, I guess, in, they do a lot of work on autism and behavioral imaging for autism, trying to like diagnose or model behavior and attention. In toddlers or kids. So I thought that was
What's an example of a model that they built?
So we have several works on so they were already doing several works on gaze estimation or attention estimation. And when I joined that group, I worked with Unji Chong, one of my collaborators, and she just graduated actually from that group. And we did behavior modeling and attention modeling in scenes. So now just more in general, like on if you're looking at a person from a third person point of view, like an image or a video of someone, you can actually detect where they're attending in the scene. Mm-hmm. And this work kind of generalizes, and you can basically detect where the person is attending to in the scene. And it could even be like if they turn their head, this could pick up that type of attention towards the back of the room, for example. Or if they're looking at the camera, they're not looking at any object inside of the scene, they're looking at something, beyond the frame, and it could also detect that type of attention. So I got really basically interested in faces, mostly just in human beings and in faces in image and video. So I think a lot of my work kind of like goes from that, and then that's how I got to recent kind of projects that I've been doing.
And how long have you been at BU?
This is my second year. So about a year and a half ago, I started my PhD with my advisor, Stan Sklarov.
What got you started working on or looking at deepfakes?
So actually, in the past year, I was always very interested in deepfakes, especially like there's a video where there's like deepfakes of Obama using a lot of computer graphics, right? They use deep neural networks and computer graphics, and this was like about like 2 or 3 years ago, there were like some big advancements. And you can see very realistic, basically reanimations of Obama's face. That already, got me very interested when I was at Georgia Tech, but I think it didn't have like the technical expertise to like really tackle it at that point. And more recently, I think the things that have been most impressive are the deepfake applications, where you only using only one image of a person, you can basically create more images or video of that person with different expressions and moving their head. And that's been like really amazing. I think there's a work by Samsung, Neural Talking Heads or something. I don't actually remember the full title, but it's just amazing how just with one image they can create these types of things. So I had been working on generative models for faces recently. And while I was working on that, I had a conversation with Stan, my advisor. There's always the privacy issue, right? Like when you're going to try to release a paper, you have all these issues that whose faces can I actually use for this work? And also kind of the reaction of the public. I think there's a lot of good that could come out of these applications, but definitely a lot of bad that can come out of them, The good part is you could have like actors in movies, you could basically edit their faces in real time and not ask them to shoot a scene again. Maybe if they like failed, in their expression wasn't perfectly what you wanted at that point. And there's a lot of different, cool applications that you can do with UI, UX and sending videos of yourself through an iPhone or something. But there's also really bad stuff that we've seen, actually. Like the first thing that started happening is, they've been using deepfakes in pornography, right? Just switching faces into pornographic scenes. And it's just, completely immoral, and the potential for damage is so big. So basically, there's always that effect. If you're publishing something on this topic, that you could be helping people that want to do bad, Mm-hmm. So that whole thing was in my head all of that time. And during a conversation, we were talking about the privacy issue. So these networks are called image translation networks. So this work by Samsung is an image translation network that goes like from one image to a new image with a different expression and pose. They also can fine tune it with like several images, but in general, that's kind of the framework that a lot of these new works are applying. So StarGAN, also StyleGAN, all of these, or Ganimation also was a I think 2017 ECCV paper, I think got best paper, basically putting new expressions on a person's face. So changing my expression from an image to be like smiling. And you've seen like applications of this in apps like FaceApp, that's become very famous. So this, image translation network is kind of simple. It's like a neural network that goes from an image to another image, and you kind of specify what the output you want it to be, basically. So, and there's all of this other work on adversarial attacks, right? That everyone has been hearing, because, you don't want to have an adversarial attack is basically an imperceptible perturbation on an image that a human being doesn't notice, but that can completely fool a neural network. Right. So, this thing has been explored since 2013 for classifiers. So if you had a neural network that tells you, hey, there's a pedestrian in the scene, or not, then you can fool this classifier. So everyone is obviously freaked out about the possibility of this, becoming a reality to attack, neural networks in the wild with this type of thing. So both of these like kind of fashionable ideas in my head, I think, it just popped out of nowhere. Like, so maybe during that conversation, maybe if we attack, an image translation network, you'll be able to protect your images from being converted into deepfakes.
The premise of this work is, it sounds like, just like in the adversarial attacks, you're injecting noise to an image, or you're injecting noise against an image and then disrupting the classifier. Here, you're trying to inject noise on an image and disrupt the ability of some generative model to do whatever it's trying to do to manipulate that image. Is that the general idea?
Yeah, exactly. So in the classifier scenario, you have an image that goes into the deep neural network, and then you want a class that comes out of it. So if it's a dog picture, you want it to classify it as a dog, right? And an attack in that situation would be to make it classify it as a cat, for example. So a wrong class, or you could be a targeted class, like you want it to actually always classified as a cat. You could do a targeted attack or an untargeted attack to like drive it away from the class, the dog class. So it could be any other class, like, lizard, the one that's closest. So the closest boundary, basically. In this case, it's kind of like a more general, it's a harder thing to quantify, right? If you have like an image translation network that goes from an image of a person, my face, like with a serious face. And then someone wants me, imagine just like, basically this is one of the types of applications for this is imagine there's a picture of me in like a serious situation, right? And I'm like a political figure or something, right? And then someone grabs this image, uses Ganimation, which is, it's working right now. You could actually use this or StarGAN or anything or CycleGAN and changes my expression into like a smiling expression, right? That's already directly an image to image deepfake that can have a lot of impact, basically. And the idea is to, make this type of transformation impossible, or basically the idea of our work is to make it either obvious or to completely disrupt the output such that it's too corrupted. It's so easy to notice that it's been corrupted, basically. So the human observer can either doubt the source of the image, or, doubt that the image has been manipulated, or can, or it's unusable, basically. It's like gibberish or black, That's basically the idea.
And so you make it sound so simple, but I'm sure, flipping through the paper, there's a lot of work that went into this. What were the challenging parts, and how did you take this from kind of idea to a working model?
Yeah, so I think actually the idea, so what I loved about the idea is that it was so simple and it was so obviously useful. That's what really got me excited at first, right? And it's actually, the first like couple of weeks of implementing all of this was actually not very hard, because the main idea of trying to destroy an output using an adversarial attack in an image translation network, it's actually, a lot of these image translation networks are very susceptible to attack. And some of them are a little bit more protected, and maybe some of our future work is going to be on that type of thing, like which architectures have more protection than others, why are some difficult to attack and why are some easier to attack, right? But the paper, so I think a lot of it went on, a lot of the work on the paper went on showing that this is possible with a lot of different types of architectures, showing a lot of very good examples that it's like a solid technique, basically. And, there are some, so basically this paper is kind of like the first, or one of the first steps into this kind of domain, because in general, so for this type of, attack, it's called a white box attack, where you need to know all of the parameters of the neural network, and you need to know the neural network that they're using, right? So that's a big, kind of if in the real world. But definitely this could work at this moment, because a lot of attacks, or a lot of deepfakes, are very low effort. So a lot of things happen where someone puts an architecture online on GitHub, right? And then promotes it on Reddit, for example. And then a lot of people go and use this architecture with this like pre-trained model, and then, create deepfakes with this architecture, right? So that's kind of low effort that can already be preempted by using this technology, because we
used to call that script kiddies. I don't know if anyone uses that term anymore.
I think we should make a new one, because
but it's the idea that like, with hacking, folks would just, download some Perl script or whatever and run it against some site to find, vulnerabilities.
Yeah, exactly. And you still had, it's funny because, I guess SQL injections were so easy to exploit in the early days, but even until like 10 years ago or something, like people were still finding SQL injection vulnerabilities. And so script kiddies kind of like were still able to like work in the real world. So I think this kind of, we should make a new term, maybe like DL kiddies or something, right? It's just people.
You heard it here first.
People trying to use like out of the box kind of stuff online.
Transfer learning kiddies.
Yeah, that's a good one.
Pre-trained model kiddies. There's something in there somewhere.
But at the same time, I always I respect anyone that tries to use these things out of the box. That's the first step, right? Out of the box from, wherever you can put your hands on any of this technology and then start using it and try to learn from it. If it's not for doing something bad, right? If it's just to learn, I encourage everyone, right, to just go on GitHub, try a bunch of stuff, and then see if they can modify it. Like, that's the way forward, right? But yeah, if you are doing deepfakes for an immoral purpose, that's definitely not good. Yeah, but this technology, so just for this specific thing, is already usable because we're able to, find. You're probably going to have the access to the weights and to the architecture, but this is a very constrained kind of attack in some sense. The more advanced types of attacks are called black box attacks. You could be like gray box, where you know the architecture, but you don't know the weights of the architecture, or there's different types of settings for that. But the black box, which is the most powerful, is just you just have a black box where you send an image and then you get an image back, or you send an image and you get like a class back, a dog or something, and then you're trying to kind of attack it without knowing almost anything about it. I think that's really interesting, and that's like where the promise lies in this, because if someone can find very good black box attacks against a lot of these methods, then you'll definitely have something that can work in the real world.
Yeah. I mean, you almost envision a scenario where, a Facebook or Twitter, Google, like when you upload a photo, it's applying this method to all of your photos so that they're not susceptible to, being used for nefarious purposes.
100%. Yeah. And that's like the first kind of application that I had in mind. The first application that I had in mind was actually for celebrities, where, their likeness is, so, it actually has a big value, right? And a lot of people are targeting their pictures to try to modify them. And that type of scenario where you can, maybe, they can buy some type of service that protects their images. And then, if you can generalize it, then you can have any type of platform online that does this. And there's just so many interesting things, right? You could give permission to someone to use your picture, and then to modify your picture, right? And then there are some, technologies that we've been thinking of in that direction as well.
Lots of blockchain opportunities in there.
I feel like... Yeah, I think a lot of people kind of jump to blockchain when they're thinking about protecting images of people or protecting media. But that's one way. This is another kind of
I jump to blockchain when I want to make a joke about overhyped technologies.
Yeah, I mean, we all fall into overhype sometimes. That's definitely true. But I also think, I don't know, sometimes it brings attention that maybe will fade, but it's still good that these kinds of domains are having a lot of attention because they have a lot of promise. And the people that stick with it are the ones that are going to make things happen. And then the people that leave, right? Okay, well, they left. And if they're not here to make something happen, then that's, their issue basically.
So is the noise that you're injecting, is it parameterized with a single epsilon value, or are there characteristics to the noise, multiple, characteristics that you're manipulating to make it work with a particular model?
Yeah, so the main attacks that we propose, and the paper is not just attacking image translation systems for deepfakes.
Okay.
It has a lot of other stuff. For example, we have you have the image translation case, but you also have the conditional case, where I don't want to lose track of your question, but I just want to say that we have basically several contributions that make it a little bit more than just, this is, a neat idea, neat little idea, right? Because I think the first kind of idea is cool, but also all the contributions that we do make this like a kind of bigger kind of type of work. Because the main idea of attacking these image translation systems, it's actually not that complicated to adapt some of the techniques that we already had. Like FGSM, fast gradient sign method, iterative FGSM. Basically, FGSM is just kind of taking a step in the direction of the gradient for your image, and then modifying your image so that you go away from the class that you want to classify this thing as. That's for the classifier case, right? In our case, you have this loss, which is you can have your main metric is what happens if you translate the image without any attack. You have kind of like a ground truth output, right? This is what the picture is going to look without any attack. And then you have a translation of your image So this is the thing that we can modify, because the translation of your image with an attack, right? That's the thing that we can modify. And now you want the difference between this ground truth output and this attacked output to be as big as possible, and with some kind of metric, right? And we use L2 in the formulation of our attacks, but you could use, a lot of different type of metrics. And we use like an image level metric, which goes like pixel to pixel differences in the using L2, right? And then you want to maximize this, right? You want your output, the attacked output, to be as different as possible as the ground truth output would have been. So you can actually just do this. It's just an optimization, problem.
Yeah, I guess one of the things that jumps to mind is, as opposed to like in L2 distance, maximizing the ability to fool some kind of discriminator network.
So we don't actually have to do that at all, actually, because so to train these types of architectures, you have a generator that does the image translation, right? And then you have a discriminator, and this type of game between the discriminator that's creating the translation and the generator, and the discriminator that's trying to detect whether it's a real or fake image, is actually what makes the output so good and makes it, approximate these distributions so well without too much blurriness, etc. That's the power of GANs. But we don't even need, we kind of like throw away the discriminator in this process, just use the generator, and it just becomes like an optimization problem.
Maybe the layer behind my question is your L2 distance is really a proxy for perceived difference from the actual face. And I'm wondering like how good L2 is for, really, making the generated image far away from the face, or, perceived, the level of perceived distortion. And so that's where I thought maybe like some kind of trained discriminator thing could be better than L2, but
that's a really good question, actually. I think you could think of like an L2 distance. You could think of the attack making just the image just a little bit brighter, and then the L2 distance would go up, right?
Right.
But so you'd have a higher L2 distance between these two, but a human being would be like, oh, it's a little bit brighter, but it's kind of still the same picture. So yeah, definitely it's not the perfect thing. In the paper, we explain why. And on average, it's a good metric to use, and we show examples. So we didn't really just go through the L1, L2 metric and be like, yeah, it's high, so it's working, right? Okay. We looked at a lot of qualitative examples, but the second, the second step that you can take after this is definitely, and I, encourage anyone that wants to try this out, actually, to try it out, because I'm trying other things. So, but if anyone wants to use like a perceptual metric, so, we have like VGG, for example, VGG trained on faces is a pretty good kind of proxy, or, it's kind of weird to say, but it's kind of a proxy of perceptual metric. So two faces that are similar in this like VGG 16 feature space are, you can actually kind of cluster them better in this type of sense, instead of using L2 metrics. So yeah, having a higher distance with a VGG, which is kind of like a discriminator in some sense. Yep. It's a neural network, right? Or you could do what you're saying is you could say, is this image, you could have like discriminator. I just had this idea right now, actually. You could have a discriminator that tells you, oh, this image is more or less distorted, right? And you train your discriminator to detect distorted images, and you train your generator to distort the images, and then you could have like a game in that way, maybe with a second discriminator as well. But definitely, like that's one of the big questions of systematizing this. Is it's easier to systematize with classifiers, because when the class is wrong. There's just a number, right? The class is 4, but we wanted 5, so it's wrong, right? In this case, you have something, and that's the problem that I've been like bumping into all over this kind of area, is you're talking about human perception and trying to kind of like model a reaction of a human being, right? Or what the human being perceives in an image. And that's, much more complex for generating faces and for disrupting deepfakes, right?
So I started a couple of questions ago asking about like how the noise is parameterized, and And I think the question behind that question was, is there, some way to just crank the noise up as much as you can before the image starts looking distorted and use that as a way, does that get you closer to a gray box or a black box type of scenario? Or do you really have to, are there, how nuanced does the noise have to be to defeat a particular system?
Yeah, that's actually a great question. One thing that I really wanted to say that I didn't get a chance to say before we started is this is not just my work, right? Like this is work with really amazing collaborators at BU. Recent research assistant professor, Sarah Del Barjal, who helped me so much with this project. And then my advisor, Stan Sklarov, right? And all of these kind of ideas have been like discussed with them. And, we've all like put so much, work into this, right? Moving on from that, basically, yeah, this is kind of like, that question is really good because one of the things that we did was try it on. So first of all, just try to see how sensitive any of these architectures is to just random noise, right? Like Gaussian noise or something. And some of them are super sensitive. I don't really want to say which ones, right? Because I don't want to just like single out any, and it's not their fault, right? But some architectures, if you inject just a little bit of random noise, then you can have very big perturbations in the output image. That was the first step, and some of them are very resistant to noise. And then this finding holds to the adversarial attack case. So an adversarial attack is just a sort of structured noise that is structured using, basically you use the gradient of the network to get the biggest type of disruption in the output possible, right? So doing an adversarial attack of same magnitude would be way more effective than just doing random noise of that same magnitude. But some architectures are just really sensitive to noise. That's another lesson of this, I think.
Your initial response to that question was talking about the broader contributions to this paper beyond the kind of the simple deepfake disruption mechanism, if that's the right way to characterize it.
Yeah, that's right.
Walk us through what you think are the biggest contributions here.
This idea of attacking image translation systems is pretty natural, but then there's some specificity of deepfake kind of image translation networks, and one of them is that you almost always have a class, or they're conditional image translation networks, and your condition could be, or your class could be, for example, in animation you have the action units, which are small movements of the face that could like correspond to like smiling or moving your lips upward, etc., right? And then by combining them you create expressions. So these networks are conditional networks, and you want to kind of attack them irrespective of the class. So my attack doesn't have to, let's just take that.
You don't want it to only work on smiling faces or something.
Exactly. Like, yeah, maybe this person is going to make everyone smile in pictures, but you don't even know what the other person's going to do. Maybe close your eyes, right? So yeah, for example, if you target an attack towards in some of these architectures, you target to attack towards one class, then it doesn't transfer to other classes as well. And in some of them, it just an attack for one class just transfers completely to the others. And I think actually these two kind of properties, like the fragility of an architecture to noise and this type of transfer, are actually related.
That sounds kind of interesting. And that is it kind of saying that the fragility isn't necessarily an architectural trait, but like more specific, like a trait of the weights of an architecture?
Yeah, I think so. I think the fragility of an architecture to attack is actually, that's what I'm like kind of discovering now, is tied not only to the type of architecture, but to the weights. And if you think about it, the weights is just a function of the training data and the training kind of process, right? So the optimization process and the training data. So these two things are pretty important, I would say. And it depends how important they are for each kind of architecture. And it's still like, this is, this is kind of like an intuition a little bit from what I've seen in my experiments. But I think there's a lot of like super interesting work to be done here, because I think adversarial attacks actually are very exciting to me. and I've just gotten into them a little bit later. But I've always like kind of wondered like how exactly do deep models work in some sense. Like, why do they fail in certain cases and they don't fail in others? This type of kind of explanatory process of the failures of a network, or how to make it better, or intuitions on how to make it better. So I think adversarial attacks are actually like a great window into fragility of an explanation of these neural networks. So that's one cool thing about this, is by attacking image translation systems, I can actually see in their output, like when I attack them, what they are doing. A lot of them. So for example, this is something good for pretty specific, I think. But for StarGAN, if you attack it, then you have the whole image that changes all at once. Mm-hmm. And you have other architectures such as animation that are very targeted towards certain parts of the image that they're modifying. So one architecture has learned how to kind of like change the whole frame at once. And then one architecture has learned to do more like fine-grained types of changes inside of an image. And one is, animation is more robust than StarGAN.
So it's almost along the lines of work like Lime and other things where you're perturbing inputs or features and seeing how the network responds to the aim of understanding explainability or producing an explanation. You're kind of almost at, trying to explain or understand these networks through the disruptions that you're injecting.
Yeah, I think so. I don't know if actually this work, I actually don't know about that work that you just mentioned, but going on from your explanation, I don't know if that has been done. Maybe it's been done for like classifiers, but I don't know if it's been done for image translation networks. And I think that's like a huge frontier that this kind of opens, is to try to understand what's going on. And then if so for example, just example off the bat, if you know that your image translation network is changing the whole frame when you actually just need to change the hair color of the person, then you could think of this as a weakness, right? And then you could think of, how do I change the architecture or the training procedure to correct this, right? And there are techniques to do it, which are pretty cool, I think. So yeah, definitely it's delving into this type of explainability. I guess that's also fashionable right now, but I think it's a huge thing. My lab does a lot of explainability in deep networks.
Okay. So this kind of broader understanding of these architectures is another contribution of the paper. What else?
Yeah. So we were on that question. Kind of easy to get lost. So that was one of our contributions, is conditional image translation networks, and building attacks that generalize to all of the different types of classes. So yeah, it doesn't just work if someone's trying to put a smile on your face. It also works when someone's trying to close your eyes in an image, right? Mm-hmm. Or it doesn't just work if someone's trying to make you, blonde or something. It works also when someone tries to make your hair darker or something. Mm-hmm. So that's one thing. The other thing is, so kind of like, okay, now we have an attack. Typical in this kind of area is you have an attack. What are the defenses, right? Like, what is someone that has like an actual like beneficial image translation network? What can they do to defend against this type of attack? Because you could also think about the scenario where, in this scenario, you're trying to, obstruct deepfakes. So you're trying to obstruct something that is done without permission of the users and that can be malicious. But you can imagine a scenario where someone attacks, let's say, I don't know, just off the top of my head, like let's say you have like an X-ray, and you have like an image translation network that makes some zones more visible to a surgeon or whatever, right? Like it's hard to come up with an example right now, but going with that example, you can imagine a malicious actor introducing one of our attacks or something like this to this X-ray to make the output not work, right? So what can a person do to defend against this? And one of the defenses that holds up to all of the scrutiny is adversarial training. I think it's done by Madry et al. In 2017. I think that's the paper. So basically, the idea is it's a very simple, very powerful idea. You have PGD, which is a very strong attack, projected gradient descent, and you just augment your data set with a lot of images that have been attacked using PGD, and then you train your neural network with those images, and it becomes more robust to these types of adversarial attacks in this type of sense that I've been explaining. And this also is, so a lot of these defense mechanisms or, defenses against adversarial attacks are so hard to make because in security, your defense has to be valid even when an attacker knows the defense you're going to use. So a lot of defenses fall apart in this scenario, and this is one that doesn't or hasn't at this point. So one of the things is it's not foolproof. We can still attack the network. So we're able to do this adversarial training for GANs, and we have like these formulations because you can train the generator with adversarial noise, but you can also train the generator and the discriminator. So you attack both the real image, but you attack the real and the fake image. So there's like different ways of doing it. The most powerful way of doing it is doing the generator plus discriminator adversarial training. And it does defend against some certain types of attacks, but so it makes it more robust. But in the end, if we have a very strong attack, it's still pretty successful. That's one thing that we learned. And in the future, more investigation in this is kind of needed to see exactly, how much robustness it does bring actually. Mm-hmm. Oh yeah, and the last one. Yeah, there's one more conjugation. I forgot. I think all of these are pretty interesting, and I would like to work on all of them. It's impossible, right? So that this one is the last one is in a certain scenario where you can blur so my advisor just told me like, oh, okay, you can attack these images. Great. But what happens in the real scenario, if you're like a malicious actor, you run into one of these images and you're like, I suspect that this one's attacked, right? So I'll just blur it a little bit with, a Gaussian blur or an average blur or something. And then maybe since the attack is high frequency structured noise on top of the image, then maybe this will destroy the attack. So that's one thing. In our scenario, it's different than the classifier scenario. In our scenario, we have to kind of also be careful of this kind of like gray box scenario where we know maybe the architecture that they're using and the weights that they're using, but we don't know what pre-processing they're using. So there are some ideas in this domain like expectation over transformation, where you just grab kind of like the expectation of all of the losses with all of the transformations that you think of. And in that paper, they did a cropping and rotating, but they didn't do blurring. So I think our paper is one of the, to the best of my knowledge, it's one that addresses blurring in this type of scenario of transferability across blurring. But also, because we noticed that blurring is actually really effective. If you blur a naive attack just a little bit, then you can definitely translate the image. And there's almost no downside because the output image looks as good.
And when you say attack here, are you speaking in the sense of kind of traditional adversarial attack or your work where you're trying to prevent manipulation, which the manipulation is kind of an attack in this.
Yeah, the terminology is actually what we tried to do is deepfake and deepfaker, right? Uh-huh. That's or manipulate, and that's the person that's trying to create the deepfake, and then attacker, and attack and disruption, right, is kind of the person that's trying to do an adversarial attack on the image to prevent the manipulation of it. Mm-hmm. So in some sense, the attacker is defending against something done onto them in this scenario, right? But it's kind of hard to keep the terms. And then the funny thing is like defense is actually the deepfaker that's trying to defend against, the attacker, right?
Right.
And in this case, actually, so in the paper for the blurring thing, we propose kind of like a different kind of iterative heuristic method, which is faster than expectation over transformation, but as effective. At least for our scenario and that experiment that we did. Expectation over transformation is great work, and all of these, honestly, all of the works that I cite in this paper are just really great and just like big steps in this kind of field. And I respect all of those people like immensely. So it's just hard to list all of the work that has kind of influenced what we do.
So the paper kind of explores these areas, and what didn't we cover yet?
I mean, I think we covered everything. One of the things is that maybe I neglected to say is that this is another really interesting kind of thing about the papers. So if you have these blurring things, so if you have different types of blur, you can have like different magnitudes of the blur, right? And every time you're attacking a different kind of blur type, you're attacking at a different type of kind of like scale. If you think about it, you're adding like higher frequency noise, and then you're adding lower and lower frequency noise. So that's why our attack is called spread spectrum attack. It kind of is inspired in spread spectrum watermarking, where you could put a watermark in a lot of different in the frequency domain, a lot of different kind of in the frequency band, basically, and not just in one, but just in a spread spectrum manner. This is kind of the idea of that defense that we present in the paper. Yeah, and just for future work, there's so much interesting stuff there.
Are you continuing work on this, or are you working on other projects now?
Yeah, definitely. So I tried to like double my efforts in this, because I feel like this is one of the projects that has really given me, a lot of ideas in so many different directions. So it's actually a little bit stressful, because there's maybe a lot of ground to cover. And if anyone is listening to this and wants to collaborate, just send me an email. You can find it on the paper, and then and we can set up a collaboration, because I think there's at least like 3 to 4 directions that are very different but also super interesting.
Well, Nathaniel, thanks so much for taking the time to share a bit about what you're working on.
Yeah, thanks so much. This is a great opportunity, and best of luck with all of your next shows and with all of this craziness that's happening right now, right?
Yeah. How are things for you? You're staying inside, staying safe, all that?
Yeah, absolutely. Like, everyone should stay inside as much as possible, and just go outside to shop or as much as you can, right? As much as life allows you.
Yeah.
But definitely here in Boston, there's nothing going on. Everything's closed, and BU has been closed. I don't know. Maybe we'll be like this for around 4 months, 3 months.
Yeah, who knows? Awesome. Well, thanks so much, and again, take care.
All right, have a good one.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.